We are at NPL, the National Physical Laboratory in London. Now this is the UK's National Metrology Institute. And if you haven't heard of NPL, it's a world-leading centre of excellence which develops and maintains the national primary measurement standards. And it also works with other national metrology institutes to maintain the international system of measurements. But we're here today to learn about one particular type of measurement using a double resonance, optically pumped Rubidium clock, which Eve is working on. So let's find Eve, who's going to take us to the lab and tell us a bit more.
This is my lab, which is one of several holdover clocks labs at NPL. A holdover clock is a smaller and more rugged atomic clock which can be easily taken off-site or kept mobile. This means that if you lose access to UTC, which is Coordinated Universal Time, then you'll still be able to have highly accurate and precise timing. This has applications on satellites, in space, and for telecoms, and enables them uninterrupted precision in position, navigation, and timing. Here are some example holdover clocks, some of which NPL worked to develop. They come in various sizes depending on their applications. And here we're showing the pulse per second output of one of the clocks. As well as overall clock development, the holdover clocks team also works on environmental testing and specific component testing. In this lab, that includes component testing of lasers, of lamps, which are useful for rubidium atomic clocks, and over on my setup, we're looking at rubidium vapour cells. This is the setup where we can test rubidium vapour cells. Before I show you too much, I'll need to go into more detail about what these cells are and the signal we want to get from them. This is a double resonant signal using both optical light from a laser and microwaves from the synthesizer. At the heart of the rubidium atomic clock is the rubidium vapour cell. These can contain rubidium-85, rubidium-87, or a combination of the two. They also often contain buffer gases such as nitrogen, helium, or argon. We heat up the rubidium to a vapour and then can interrogate it with laser light, microwaves, and magnetic field. To understand how that works, let's have a look at the energy levels. As Andrew stated, we use the principle of double resonance optical pumping. So first let's look at the optical pumping done by the laser. In this experiment, we specifically lock to this transition, which is f equals 1 in the s orbital to f equals 2 in the p orbital. This excites electrons out of this lowest level up to here, and then they relax in equal amounts into these two levels. Because we are continually emptying this f equals 1 level and filling f equals 2, we end up with a population inversion. The second transition we need to look at is the clock transition, which corresponds to a microwave frequency. Under microwave interaction, electrons are moved from the f equals 2 level back down to the f equals 1 level, where they are then available for further optical pumping. So why do we need both of these transitions? The answer is detection. The clock transition corresponds to a microwave frequency, which is not that easy to measure on its own. However, it's very easy to measure optical absorption with a photodetector. When we just have the laser, we are emptying out this f equals 1 level, and all the electrons get trapped in f equals 2. This means that after a certain point, we get no further absorption of the laser light. However, if the microwave is also resonant, then f equals 1 is repopulated and we can continue optically pumping. This means that laser light is absorbed by the rubidium vapour. When we sweep the frequency, we find that we only get a signal when both the microwave and optical frequencies are resonant, and this is why this is our double resonant optically pumped signal. First, we have our laser, which is locked to a specific frequency using a rubidium reference cell. And we can measure that frequency using a wave meter. The laser is directed using a fibre optic to our optic setup. We send it to the reference cell and the wave meter, and then onto our physics packages. You may be wondering why you can't see anything, and that's because at this frequency the light is infrared. Now we have these two physics packages where we can test our cells. The one on the right contains the cell that we're going to be looking at today and is at a temperature of 90 degrees C. However, we can have a look in the one on the left to show you what's inside. Before I do, we'll also mention the microwave synthesizer, which is scanning our microwave frequency. This is externally referenced to one of MPL's hydrogen masers to make sure that those frequencies are accurate. Inside the layers of shielding and thermal insulation, we have the microwave cavity. This is a fairly simple cavity design, but you can engineer cavities to better amplify and focus the microwaves, such as the magnetron type cavity that we have in the other physics package. This cavity has our heater around the outside, and then on the front face we have a hole for the laser light to pass through and an antenna that receives the microwaves from the synthesizer. We also have a cell holder which places the cell in the centre of the cavity, where it can then be interrogated by both microwave and optical radiation. With all of these elements, we can get our drop signal. We use an oscilloscope to take the photodetector signal from the back of the physics package. You may notice that this is a slightly strange looking line shape. That's because there are actually 7 features caused by the Zeeman splitting of the energy levels. Under a magnetic field, the F equals 1 level splits into 3 and the F equals 2 level splits into 5. This gives us 9 allowed transitions, of which there are 2 pairs that are energetically equivalent, leading to 7 features. Now if we apply an extra magnetic field from Helmholtz coils, we can see these features split out, and if we increase that magnetic field, their separation in terms of energy and therefore frequency increases. The feature that we're interested in is the one in the centre, because this takes place between 2 levels that are magnetic field independent. This means that if the magnetic field changes, their energy and their frequency does not, and that makes these more suitable for an atomic clock. To use the drop signal as a frequency reference in an atomic clock, we need to lock the microwaves at the point where there is maximum absorption of the laser light. We can modulate this signal and get feedback, which we use to discipline a crystal oscillator. To get the best stability of this clock, the signal needs to have a good signal-to-noise ratio and a narrow line width. These are what we're analysing for our cells, because it depends on things such as buffer gas, rubidium content, and cell size. This helps us to develop better cells with our industry partners and to determine which cells are the best for different applications where we may want a clock that is smaller, lower power, or more resistant to environmental conditions.
Well, I hope you guys enjoyed that as much as I did. It's my first time here at MPL, visiting Eve, and the whole place is like Christmas for nerds, if I'm honest. It's been a great visit, so thanks Eve for telling us about your project.
Well, thank you for coming. It's been really cool to talk about some of the stuff we do here that people don't normally see, and to bring together 2 different things that I work on.
And if you'd like to see more videos featuring Eve, do check out some of the previous content on the channel. Now hopefully we'll have some more stuff from MPL coming soon, but in the meantime, please check out MPL's YouTube channel, for which there is a link in the description below.
See you next time.